computation and for arranging everything. So this will be a talk about 2D gravity. It's work done with Jan Trost at École Normale, and this came out over the summer this year. So I'm not an expert in this area. I should send a disclaimer. So let me first summarize the main result of this work. So the main idea is already mentioned in a paper in 2003 by Agenagich, Digraph, Clem Marino, and Wafa, where they say that suppose you start with a closed string background and you want to add a D-brane with some open string modulus S. You want to rewrite that as a purely closed string partition function where the background gets shifted by an amount that sort of depends on this open string modulus in some way. So this is the basic idea, that you have some closed string background that solves the string equations of motion. You introduce a D-brane into the system, and then you want to write this open plus closed system as a purely closed string system. So this equation you can see there if you look up this paper. And what we want to do is to make this completely precise in the case of 2D gravity, where the closed string theory is completely solved. And what we found can be summarized by this simple.
Really sorry.
Sure.
Because I came in late. So just
No problem.
why do you expect to write the open closed as purely closed? Because in a rough sense you include the D-brane.
Maybe the back reaction is
back
yeah,
background.
exactly.
Okay, thank you.
Yeah.
What is lambda? Capital lambda?
Lambda describes the closed string background in some sense. So I'll describe.
Before you put the D-brane.
Before I put the D-brane. So I'm setting that to 0 here. So it's like saying I have no Raman flux in flat space. I put a D-brane, I take some back reaction, and here I have Raman flux turned on in the fat case.
So Z is 0, 0, that's 0 for S equals 0, right? On the right hand side, and just not confused about notation. This 0?
This 0 is lambda equals 0.
Lambda equals 0.
So the closed string background, there's some parameter that is set to 0. And I'm saying that some closed string parameter is turned on because I have an open string whose reaction I've taken to. But what we found in this case is that, in fact, it's a bit more complicated than this. That if you add a D-brane to this closed string background and you take and you rewrite that as another closed string partition function, we found that the background gets shifted as you expect from here, but the partition function gets some renormalization. There's some prefactor apart from what you would expect. And lastly, it's not a direct product like this, but it's really an integral transform.
Okay. You found that they were wrong, basically.
I wouldn't say that. No, but I mean, this is the intuition. I mean, in that.
Yeah.
Yeah. Anyway.
I think the non-trivial thing, okay, the renormalization is interesting, but non-trivial thing is it's some integral transform.
Integral transform, yeah, exactly. So we're not the first people to do this. So this was first obtained by a couple of mathematicians for pure gravity in this form. So this left-hand side is, so let me go back a minute. So we're considering topological gravity. So 2D gravity is the same as topological gravity in D equals 2. We couple it with some C less than 1 matter. So the entire thing is still topological. And we have some closed string partition function to start with. I introduce a D-brane. So this on the right I have an open plus closed partition function. Lambda is some closed string background and S is some open string modulus. And the statement is that it's related by some integral transform. I'll explain what the FT is, some generalized Fourier transform to some purely closed string partition function. Okay, so these Z and S are these.
DZZ or ZZ, all these brains.
Exactly, but we will not use the.
Oh, but you have some topological.
FZZ.
FZZ.
FZZ. Yeah.
Sorry, I'm the only one in the audience.
And the same result was obtained by Digraph and Witten recently, but using some different methods related to chiral bosons and so on.
X stands for what?
Extended. So some extended closed string partition function. I'll explain all these things in a moment. So this is the main result. So that's the take-home message. Okay, so I'm going to give you a very brief introduction to 2D gravity.
If you don't mind, even before you go
Yeah.
into the details, just you're putting just one D-brane.
In this case, it's one D-brane, yeah.
So for a non-topological theory, we
You
don't
wouldn't
normally
expect this, yeah.
one D-brane to be
No,
closed strings.
no.
But because it's topological,
Exactly.
Curvature is not important, something like
Exactly,
that.
exactly. Yeah, that's very important.
Yeah.
Okay, so there are many different ways to solve 2D quantum gravity. So I will not talk about old matrix models apart from the slides. I just want to summarize what's known. So this is what is called the discrete approach to 2D gravity, where you study an auxiliary matrix model with some cubic interaction like so, and you expand the partition function in G and 1 by n.
So in the open string side,
you will have matter coupled to gravity roughly.
But this is topological matter again. I wouldn't, yeah.
But
This-
this is still not, in some sense, I'm asking, it's still not unitary because it's non-critical and so on.
Now, this is an integrable system, as I will show. It's completely
But
solid system.
it's not unitary, so because it's interesting from other perspective that you couple gravity with matter
Yeah.
and try to understand that system from information patterns. But presumably this is not.
No, I'm not going there at all.
But this is not the system that you like to study because probably it's not unitary. Non-critical is.
Why do you say it's not unitary?
Yeah.
Because it will not have all the right properties of modular invariance and so on probably.
There was this window, right? It's between 1 and 25.
Yeah. This one is C less than 1, so it's fine.
But the gravity part.
That's perfectly fine. I mean, the partition function in 2D is well defined.
Yeah.
It's a modular invariant in that it preserves large gauge transformation.
Okay, so then we can take even this system and calculate 2-point functions. Later, not for you.
What the 2-point function means in a theory of gravity is another story. That
If you have a boundary.
oh yeah, then you can do stuff.
Yeah, I think we should.
I'm just trying to get into this.
That's a
We will get into it slowly. I just want to give a background to people who are not familiar with this, so I'll just give a few slides on. Maybe.
Sorry for the can I pick up it as a FCC brain in Siga geometry?
We will come to that. Hold on. Okay, so the idea, so if you take the naive Largen limit, what people found was that there is a critical coupling at which the perturbation expansion diverges. And this is supposed to be the continuum limit of the model. And so what people did, but you see there, you are stuck to the sphere partition function, the genus 0 contribution. So if you want all genera to contribute, what people did was to take a double scaling limit, where you take n to infinity, you tune g to this critical value, and you keep some combination fixed, okay, which depends on this the critical exponent, this KPZ scaling and so on. And then you compute the partition function of the matrix model. And this was solved in the 80s by these three groups. And so a lot of things. So the goal is to compute correlation functions of trace n to the k. Those are your observables. And all of those can be computed in this double scaling limit. And that's supposed to describe quantum gravity. Okay? I haven't described how, but this is going to capture that. So this is not the approach I'm going to follow.
And sorry, you won't follow, but just to understand,
Uh-huh.
there's some coupling constant in the end, right? That is, if I remember that, you take G to GC and
Yes.
N to keeping something fixed.
Yes.
And you have the analog of that in your topological, presumably. Is there an analog of that coupling constant in there?
We will
To
see.
expand?
Yeah, so there's some genus coupling parameter,
Yeah.
there is, but there is much more.
There's much more.
There's much more. So what happens is, so there's this another approach to the gravity, which is topological gravity, and which goes by the name of intersection theory on the moduli space of curves.
And so far, there's no matter.
There's no matter. This is just pure topological. Exactly. Yeah. So this is an approach that was pioneered by Witten and later solved by Kontsevich. And there the idea is to define some differential forms on the moduli space of Riemann surfaces and study the intersection theory on this space. So you study the intersection of these forms on the moduli space, and those are your basic observables. Okay. So what Witten does is to define this formal generating function, what he calls f of dk, where each of these t's couples to these observables sigma k. So these are your observables in this topological gravity, and they contribute at a particular genus where this condition is satisfied. This is essentially saying that you want a top form on your manifold. You know the dimension of moduli space of Riemann surfaces, and so you compute a formal generating function like so. And Witten's conjecture was that this partition function satisfies this partition function is a tau function of what is called the KdV hierarchy. So there's some integrable system that underlies this 2D topological gravity, and the Z is identified with the partition function of the 2D gravity, quantum gravity that I defined on the previous slide.
Sorry,
Yeah.
I know nothing about this, I'm embarrassed, but the expectation value is taken by using some action or
No, this is just intersection of some differential forms on this moduli space. We know the dimension of the moduli space. Each of these are like two forms, roughly speaking. So you know when the top form is reached, essentially. That's it. So it's some formal mathematical way to define topological gravity. So we'll get back to this integrability story later, but the main takeaway from this slide is that this Z defined in this formal way to the F, where F is this generating function, coincides with that you compute from the matrix models. Quantum gravity, let's say, is the old matrix model definition, where you write the action to be root gr and so on. Okay, I'll come to this in just a second. So this is one approach. Some matrix model is a discrete approach to quantum gravity. This is the topological approach. So let me just stick with this topological approach a moment and stick with this partition function, this generating function f. After this conjecture was made, this was solved by Kontsevich. Sorry, no.
If you don't mind.
No.
So the right-hand side of that equation is just some simple geometry stuff.
Yes.
So when you say it was conjectured to be this KTB dihierarchy, you could probably just prove that, right, or not?
No, see, he proved it for the first few cases. He checked this for the first few. This is a whole infinite set of equations for all time. So for the first few, he computed the partition function at genus 0 and so on. I could check it.
Right.
But it's not clear that for all genus it's going to work.
I
like
see,
this.
but it's just a matter of computing some intersections of
Exactly.
some simple geometry.
Exactly. Well, simple one.
mathematics.
Yeah.
Okay, fine. And then you said that Z is going to coincide with the partition function of the matrix model.
Right.
So now this guy has
So-
lots of coupling constants.
Right. So sigma k should be identified with phrase n to the k, roughly speaking, in the old matrix model. Exactly. So these are just what I call gravitational descendants and so on. They map to these operators on the matrix models. Okay. So after this conjecture, almost immediately afterwards, this conjecture was proven by Kontsevich, who used yet another matrix model, which is now called the Kontsevich matrix model, to solve this theory. He said that this f can be computed by computing this integral. So this looks a bit complicated, but essentially what this symbol means is that you expand this out as a binomial coefficients, and you keep only those terms which m greater than or equal to 2. So when p equals 2, you essentially get m cube and m squared term. So this lambda is this source which somehow encodes all the tks that I defined earlier. It encodes all the couplings to all these operators. Yeah. Okay, so these are what I call matrix array integrals. They are by now very well studied, but he was the first person to introduce this. So the claim is this tau of lambda is essentially where am I? F. Sorry, is essentially Z. So is this point clear? So I'm introducing an old matrix model, which I'm not going to talk about. Then there is this intersection theory and moduli space, which also I want to talk about. But that's same as this, and this is what I want to talk about.
But this comes from the first slide and this slide. If you, I mean,
Yeah. So he had a way to.
this connection can happen directly without using the instance.
It can. So what Kontsevich did was to write down what he called the cell decomposition of moduli space of Riemann surfaces, and he showed that using combinatorics, he computed the partition function.
But just at the level of matrix model, this can be not seen.
Yeah. So if you do the perturbation theory here, you can see the Riemann surfaces essentially being made by the fat graphs of this matrix model. So let me just tell you what the exact identification is.
If you don't mind,
Not at all.
one transparency. The written stuff.
Yeah.
This was a formula generating differential forms in the moduli space of Riemann surfaces of all genuses.
All genus and all yeah, exactly. All genus.
Thank you.
I mean, you see, this was motivated by the solution of the old matrix model, because the old matrix model, they already found the KDB hierarchy.
Right.
And then he knew that this was that topological gravity and quantum gravity is the same in 2D.
Yeah.
So he conjectured that this should be true on this math problem as well. I think.
Yeah, but then to relate it to differential forms on the moduli space.
Yeah, you need to be somebody. Jump. Okay, so what Kontsevich showed was that tau of lambda, what I defined as this ratio of this matrix model.
Sorry,
Yeah.
I'm really sorry.
No.
To go back to Arjit's question, at least it seems like a mere model might be able to take, if you go one slide back to Kontsevich's, to take this definition and relate it to your first matrix,
No,
even mere models.
No, no,
I see.
no, it's not obvious how you go for the old matrix models from this.
I
It's
see.
not.
I mean, this seems like a matrix model. That seems like one can't.
No, but see, there's a double scaling limit. Here, there's nothing. It's just an ordinary matrix model. That's the key. That's why it's much simpler to work with this. Okay. So the matrix source is related to Witten's T case, the ones that coupled to the sigma case, by this relation. This is what Kontsevich showed. And these are the same parameters that couple to the operator sigma k. And as we'll find out, and this will be useful for us later, these Tk are what I call the times of the KDB hierarchy. So KDB hierarchy has this infinite set of times. I'll again explain this later on, but these are all the same thing. Okay. So I hope this setup is clear. Okay, now let's go ahead. Well, the good thing for us is that all of these approaches have the source in string theory. It's a very simple way to understand it, at least in words. So the third approach is, of course, to couple Liouville theory to matter and define that to be quantum gravity. I think this is what you were asking. And the nice thing is the natural interpretation of all these matrix models from the point of view of string theory, and they're all world volume theories on some d-branes. This was first shown by McGreevy and Verlinde, where they showed that this double scale matrix model is kind of localized, is the world volume theory on localized branes in Liouville. And that this was shown by Gaeto and Rastelli that the Kontsevich model is in fact the theory. In fact, they show that the open string field theory on FZZT branes is the Kontsevich matrix model. Okay? So we'll mostly focus on this. So we'll work entirely with the Kontsevich matrix model, but we'll use all the intuition that comes from this identification. Okay?
So you're saying it's ADS?
I would like to, yeah, I don't say that, but
Kontsevich is the brains,
yes.
and the other side is the clusters.
Exactly. So what we want to do is to show open-closed duality. And now that we have this interpretation, it's very simple what you have to do. What you want to show is that what plays an important role is the fact that the integration variables in the Kontsevich matrix models correspond to open strings. They're like mesons just between FZZ and ZZ branes. This was an interpretation that was given after the Gaeto-Rastelli paper in these set of papers. And once you know that, open-closed duality is very simple, because what you want to do is to separate out one brane, right, and then treat that as a probe of the closed string background.
So once again, this is like ADS, right? Open strings are fields.
Exactly. So that's the same intuition, but here is everything is solvable, and you can just work. You can just do the result for a single brane.
So when you say closed string is from this old quantum gravity point of view, the worldsheet? Is it the worldsheet of that?
Yes.
The other matrix model is just a way of computing that.
Yeah.
Why worldsheet? I thought space-time. It's 2D gravity.
2D
I'm just confused. Oh, sorry, I thought you had one description which forget Witten's, which confuses me, but at least 2D gravity.
No, I think you're right. Yeah.
Is space-time.
Yeah. So C less than one matter coupled to Liouville. Yeah. So maybe sorry. Yeah.
I mean, your comments were
But you don't have a space-time dimension at all. It's not like C equals 1 matrix. It's C less than 1. So there's almost
No, but
there's no.
what I was saying was that conceptually in the terms of ADS CFT,
It's 2D gravity. Yeah.
in 2D,
It's not the
and
worldsheet
some
thing. Sorry. Yeah.
matter.
Yeah.
That matter is C less, but that's fine. You
Yeah.
can have any kind of matter in 2D.
2D gravity in space.
You will
Yes.
do this.
Yes.
Now, whether that bulk theory has a worldsheet interpretation, okay, that's another issue.
Yeah. Okay.
That was in your previous slide.
Yes. So this you would start with this. Yeah.
C less than one matter plus Liouville.
Yeah.
So there is a worldsheet description.
This is space-time. What
Yeah,
I'm
so-
saying is this is space-time.
So yeah, but I should say that this C less than 1 matter coupled to Liouville, it was analyzed by again a couple of mathematicians, Lien and Zuckerman, who computed the BRST cohomology of this worldsheet theory, and they found operators that match this sigma k description. Liouville theory is on the worldsheet, exactly.
It's a
Yeah.
non-critical worldsheet.
Exactly.
But I normally think of Liouville theory as the space-time 2D theory dual to matrix. I mean, you have an interpretation of Liouville theory just as the space-time, because that matrix model describes 2D gravity, right? And 2D gravity also has a description in terms of Liouville theory.
Yeah, but I don't.
You can go to conformal.
No, here I'm talking about just some worldsheet operators that look like e to the some discrete alpha times phi times some v matter. So I'm saying the sigma k will be some operators in the BRST cohomology of this worldsheet CFT.
Phi is the
But it's topological matter. So you take some LG model or something, C less than 1, and you keep just the chiral ring elements.
And isn't the Liouville coming just because you have C less than?
Exactly, yeah. You just have,
in the old developments of David, Distler, Kawai, and so on.
Yes.
This was space-time. There was 2D space-time, and you went to conformal gauge,
yes.
and so you had a scalar,
Mm-hmm.
and then you could couple that to any kind of matter. And if you took the matter to lie outside of in that window 1 to 25, you got crazy exponents. Otherwise, you got reasonable exponents, and so on. So there was a way to dress every field
Yes.
to make it generally coordinate invariant from the 2D gravity point of view. So this was a consistent 2D theory of quantum gravity. And
That's
what matrix theory describes. Okay, never mind, go on. And I thought, therefore, what you were doing was describing the duality between that, and you could put branes in space-time.
yes, that's all true.
Which was FZZ branes and so on, and then etc. etc. I thought that's what.
I don't know the story very well. But suppose we did C equals 1, C equals 1 theory. Then we get one scalar and the Liouville mode.
Yeah.
Right. So this Liouville mode appears on the worldsheet, but it has an interpretation as a space-time coordinate.
You can say that. So it's confusing because your worldsheet is also 2D and your space-time is also 2D.
Right.
But I'm just saying, okay, right. There's a way to think about it where.
Fine. No, I agree. I think it's just the usual thing, but the space-time and the worldsheet have the same fields.
Yeah.
I think so. Yeah.
Okay, all I was saying was that you can just think of it really as space-time with the Liouville field being the conformal.
You're saying space-time with a linear derivative.
Yeah.
For instance, could say that. Yeah. Okay, so what we're going to do is to exploit this interpretation of the degrees of freedom of the Kontsevich model as open strings. And what we'll do is to do a probe-in analysis in string theory language. So what we're going to do is to start with the Kontsevich model, which describes the closed string background, and just integrate out one eigenvalue. So what we'll do is to take this matrix. So you have this M matrix, like so, and what we'll do is to integrate out these massive degrees of freedom, this last block, and write everything as an integral over this last eigenvalue. No, that's a good question. In principle, the analysis is true at finite n, but can I go back a few slides? Sorry, I hate doing this. You see, all times are independent in the topological gravity. So, it only makes sense strictly in the large n limit of the matrix. It's only in the large n that all traces become independent. So, although you can do the analysis at finite n, if you want all times to be independent, but if you turn on a subset of times, you have to have the matrix such that it's bigger than that at least. That much is clear. So, yeah. Is that? Okay. Thanks. That was a good point. Okay, so as I said right at the beginning, the calculation is completely elementary because you have a matrix model with a simple action. We integrate out these degrees of freedom and write an integral for this mode.
By moving this mode away from the others or not?
I mean, in principle, yes, yeah. So we want to write an effective action for this mode, roughly speaking.
After moving it away?
Yeah,
There's no such notion.
No such notion, right? It's just a matrix integral, so it's quite simple. And finally, we get some result, and this is like a few pages of technical detail, but after that, most of the time will be spent trying to understand what the quantities we get on the left and the right are. And for that, we have to take a digression towards this KDV hierarchy, so I'll give a short detour about that. Okay, so this is the plan. I'll start with the Kontsevich model now and just do this integration out. And then we'll get some result, and then we'll try to interpret it using integral systems. Okay?
Kontsevich matrix model partition function was demonstrated to be the partition function on the brane.
Yes, on the FZZ branes, yeah, exactly. FZZ branes, that was the pure gravity case. And then these papers by Hashimoto, Huang, Clem, and Shi, for the case with matter, they showed that, in fact, you should really interpret them as sort of mesons between ZZ and FZZ branes. In this probe picture, I think that's the best way to think about them. These guys did it for pure gravity, and these guys generalized it to the coupled to matter case. Okay, so let's start with this technical analysis. It's not terribly long, so I'm just repeating myself here. So you see, what you do is to
you insert some operators and not just partition function from matrix model perspective, right? You will insert some.
No.
You just take only the partition function of the matrix model.
Yes, we will derive an insertion at the end, as we'll see. Because you can't, I have to start with the closed string system, and that's it. I start with the closed string system. So what I do is to start with n plus 1 eigenvalues. I call the last one z.
This is supposed to be the closed string part now.
It is.
Okay.
Let me go ahead and you'll see. Hopefully your questions will be answered. Okay. So you start with n plus 1 eigenvalues of this source, matrix source. And I want to calculate this partition function, which is that of the Kontsevich matrix model. And as I said, we just integrate out this 2n to n block. And then we'll be left with an integral over a single n plus 1 eigenvalue. You see, we don't have to do the integral. I want to write it as integral over this last eigenvalue times what we had earlier. Okay, so it will be all quite simple. Okay, so let's start with the denominator first. It's completely trivial because just a Gaussian integral. I have 2 m's in the exponent.
If you don't mind,
Not at all.
you're just going a bit too fast.
Sorry, please.
So the matrix integral was matrix over n, and lambda was some fixed guy, right?
Lambda is a source.
Yeah.
And you should think of lambda always as saying that this trace lambda to the minus k is my tk. So these are my sources.
Yeah. So lambda is something fixed in the process.
Exactly. Exactly.
Now you split up this m integral into what did you say that we split?
So I split them into these n by n block
Yes.
and a 1 by n if you wish, these whole blocks. And then I'll integrate over all these guys except the last eigenvalue.
Okay.
And what allows me to do that is some technical results in matrix integrals.
Okay.
Basically, what this is supposed to give us now,
So
this
is it-
entire matrix model, which would
So this is the partition function of in the presence of only these sources turned down somehow.
but also the effect of gravity, right? A little bit of
This whole thing is a partition function is the closed string partition function. So this Kontsevich matrix model, although the degrees of freedom are open strings, right? The result is a partition function of purely closed strings. There is no open string modulus here. All these lambdas are related to closed string moduli. They are giving what the background is in this sense. So you see, it's the ideal situation where the sorry.
I should not think of this as a boundary case.
No, I don't know if the yeah.
No, but why not? Isn't this like ADS-CFT where you can
Where,
compute the
if you wish, yeah, where I have an integral over using open string degrees of freedom, and the result giving me a closed string answer. So yeah, so maybe it's fine to say that.
If I do that, then integrating this out would mean that
I've-
this system of brains is living in a gravitational background.
Yes. So what I want to do is to understand. I'm sort of doing the reverse. Ideally, you would like to add a brain and check this, but here I'm sort of removing a brain and trying to do the reverse somehow. That's all.
I thought it's a little bit like this. Since you have a integral equation couple which includes the expectation values of the TKs,
Yes.
which are like closed string sources.
Yes.
Right? Now, if you wanted to introduce a D-brain in the bulk, you will trigger some expectation value for some source term.
That's right. So here I'm doing it in reverse somehow. I'm starting with a bigger. I don't know the answer. I know the n plus 1 answer. I know the effect of adding it. Then I'm sort of extracting 1 out and then saying how is it related to the 1 with just n.
Yeah, I understand, but I'm just saying this is what you would do if you just had the
If you
open
yes,
string
if you had
description,
yes.
and you were trying to introduce the brain in the bulk.
Yes,
and
I'm not doing that. Like, I mean, effectively I'm doing that, but in reverse order somehow.
Okay, go ahead.
Because here he knows the open string kind of had some, because he can do that integration and make it a matrix model.
No,
So this is the
I understand. I'm just saying if you just had the Young-Mills theory,
Yeah.
and you wanted to say how would it behave if I introduced the D3 brain in the bulk.
Yes.
That's what you would do. You trigger
I would-
the
that's what I
source
would do.
for some trace phi squared,
Yes, yes, yes.
phi to the n, and see how it does.
Yes,
right?
yes.
That's what
That
he's
would
doing.
be like
I think.
integrating out the rest of the thing to get an action
It's
for
the
one.
opposite.
Shiraz, can I go ahead or is it no, no.
No, I'm happy. I just have one
Okay.
comment after that.
I mean, sometimes one would also want to integrate this n by n block, right?
Sometimes you would want to integrate
The n by n block out.
n by n block.
For
Oh.
just the brain, no? So that you could think of this as a brain in the bulk.
No, see yeah, that's true. But I don't want just the purely open one. What I want is the, how can I say? I want some purely closed string with something that I'll find out what it is, and then I want here open plus closed. So I'm keeping all the lambda. So this is the lambda if you wish, and this is like the in some sense.
I'm probably repeating what many people said, but in Dwan's original paper, he talked about how the action for one D3 brain in ADS would be the same as the action on the Coulomb branch
Yes.
of taking one brain away from the rest and integrating out.
That's right.
That sounds.
It's similar, exactly. Similar in spirit, I would say.
That would be the integrating out a big block, right?
Yeah, in some sense, yes. Yes.
And the off time.
Yes.
You want just
He just wants this.
Yes.
That's what he was saying earlier. Yeah.
That's what, yeah. When this is that, then we're not.
No, we're not doing that. So I will keep everything as it is. Yeah.
You're not doing that. I thought you were integrating out everything but one eigenvalue.
No,
No, I'm integrating only this, only the mass, only the
Okay,
off-time.
thank you. Yeah.
But in principle, you could also integrate out n by n block. If you wanted
I wouldn't know how to do the integral, but yeah.
But in
Technically, I
principle-
wouldn't. In principle, yeah.
Then it would be exactly like what null scenario.
Yeah, that's right.
So here you choose to keep n by n.
Okay, fine.
You're saying you want the theory on the brain. Is that the, okay? Yeah. Okay. Yeah, we haven't done that. That's a good question.
Physically, I don't quite understand what is the right side.
We'll get there. Because here everything is close to degrees of freedom at the moment. Okay, so now let me start with the denominator, which is very simple. It's just a Gaussian integral, and the coefficient of the Gaussian in the exponent is just some binomial series, so I write it like so. I'm just showing the calculation to show the spirit of what we're doing. So here this lambda z is the guy with n plus 1. So what I do is to just write everything in terms of the n by n lambda and z. And this d of lambda is what you would write if I had just the n by n determinant, n by n denominator. Yeah, so you see, lambda z is like lambda z I, n plus 1 of them. Sorry, terrible, yeah. I goes from 1 to n plus 1, and n plus 1 guy is z.
Because you had some transpose between z and I. That's why I was lambda z comma j to the t minus lambda I comma z.
Could be a typo, I'm sorry. Yeah, it's a typo, sorry. Yeah. So essentially, what I will do is write the entire partition function like this. I want some f of z and lambda, and then some d of lambda. Okay. So the integrating out is a bit complicated for the numerator, and let's just try to sketch how it's done. So after you shift the lambda by some z dependent source, what you find, sorry, after you shift the m by a lambda dependent shift, what happens is you get this. So you see, this is why I said it's a matrix Airy integral. If you just had p equals 2, you would have an Airy integral, exactly, with matrix degrees of freedom. So the idea is the following. We first diagonalize this by a unitary transformation, and this diagonal MD I'll denote by these MIs, and you just get a van der Waals determinant as the change of variables. So you have the integration over the eigenvalues and the angular variables of the matrix, as you'd expect. And you have this. So this is completely trivial. And here I have some non-trivial integral over n plus 1 degrees of freedom, angular degrees of freedom, with a u and a u inverse appearing there. Okay.
So that's an n-dimensional integral
Okay, dimensions I'll have to
or n squared.
order of n square, because this is n plus 1 whole square, this is minus n plus 1, so whatever is left is angular. Sorry.
No, I mean, is it this block only, or it's actually what is
No, you're just removing the diagonals, and everything else you're integrating over here. Okay. So it's almost the whole matrix except the diagonals. And now I use what is called the Harish Chandra Itzix and Zubair formula, which is a very lovely formula that tells you exactly how to do this integral in closed form, like so. But you see, I don't want the final answer. What I want to do is to separate out just one eigenvalue out, right, and write what I had earlier and see what extra insertions in the path integral I actually get, matrix integral I actually get. So I first isolate the integral over the,
Let me just understand.
yeah.
So little AIs are what now?
So these are so A and B are diagonal matrices. So they are like my lambdas in my previous slide. So AIs and Bj's are these eigenvalues of A and B. So I just use the formula first, and then I isolate the integral over the n plus 1th eigenvalue of m here. I want to isolate that guy out. Okay, and then I use the Harish Chandra formula in reverse and write it as an n by n integral. So this is a technical computation. I'm not going to go into the details. You can do this. And at the end, you see what I get is I can, again, using this back, I can write now in terms of n angular variables instead of n plus 1. So effectively what I'm integrating over these guys. I'm not showing you how I'm doing it. It's there in the paper, but the idea hopefully is clear. And the numerator looks like this. I have some s integral with the same exponent I had earlier, m integral like so, but now I have a determinant insertion. I get a nice determinant factor that somehow is the, so this s is the n plus 1 eigenvalue.
If you don't mind, interrupt just to make sure I'm understanding the picture. So the idea is that there is this integral over n cross n matrices that will give you the closed string answer.
Exactly.
But you will get the same answer if you did n plus n or n plus 1 cross n plus 1.
Exactly.
So we'll do n plus 1 times n plus 1 and split it into an n plus n,
Yeah.
which is the closed string answer,
Yes.
times whatever's left.
And I want to interpret that as
Then
the
you get closed string
open
is
plus
equal to
closed.
string times
But it doesn't factorize because you see,
Doesn't
it
factorize.
doesn't factorize.
Fine.
Exactly. So this method is adapted from Burek and Tesla, I should say, but they only did it for p equals 2. And if you blindly did their case, you won't be able to do this, use this formula. So we have some slight shifts and changes the variables, but the model is the same. They did have the idea first, so I should give credit where it's due.
Is this corner, S is this corner?
Exactly. S is the n plus first eigenvalue. Okay. So let me put everything together.
So just to be sure, in the first line, the determinant of e to the alpha aibj, I mean, what does that mean? I mean, aibj are entries.
Entries. Exactly.
No, I mean, what is the matrix? I mean, what is
So the ijth entries is that guy. Is so e to the alpha a1 b1 is one entry, a1 b2 is.
does it mean just e to the alpha ab in the?
No, I'm saying the entry will be something like e to the alpha.
Oh, I see. Okay.
That's all the way.
Okay. Thank you.
So, and so the thing that seems remarkable is that is it right that this Kontsevich formula was supposed to hold for all n greater than something?
Yeah. So if you have only some p's turned down,
Yes.
then you need a matrix that is bigger than those t's. Yeah.
And then every n larger than that
Yes.
will give the same answer.
That's the claim. Yeah.
That is the incredible part. That's what allows you to say
To
n
go
and n plus 1
are the same
are
somehow.
not the same.
Yeah.
That's the physics, and then
Yeah.
you process.
Exactly.
For
Yeah.
low P's, you would expect that for several matrix models. I mean, it will start differing only for large, small matrices. If the
Why don't you have 1 by n expansion for every quantity? The partition function itself has a 1 by n expansion.
well, okay, I'm deriving this from this index type matrix model intuition, where the index for SU 100
Uh-huh.
is the same as the index for SU infinity.
Uh-huh.
You're only looking at small operators.
But it seems to be some feature, I mean, if I can echo Shiraz, of the topological theory, because if you take trace phi to the n,
Uh-huh.
its expectation value depends on the rank of SUN.
That's true.
So
Yeah.
the fact that it doesn't is kind of nice.
Yeah, but I mean, strictly speaking, you should think of the Kontsevich matrix models as being strictly in the large n limit. You should take it for independent of traces, but as you said,
But you can, for certain things,
you can.
do a SU10
Yes.
and SU11 will give the same answer.
Yeah.
And that's what you're using.
that's what I'm using. Yeah, I agree.
Yeah.
Okay, so this is the answer that you get for the numerator. If you put everything together, what you'll get is this formula, which is nice but a bit messy. But what we'll try to argue is that the right expression to describe open-closed duality is to multiply this factor on the left and treat this as what I call the extended closed string partition function, and this integral, just this box integral, as an open plus closed partition function, where this S is now interpreted as an open string modulus. So this is like, that's why the FZZ brain has one modulus, and that's exactly this guy. It's here. And you see what I said at the beginning, that I have some extended partition function, I have some open plus closed partition function, is closed and open, and then related by this integral transform. So again, it's like a higher airy type integral, and that's it. Okay, I hope the result is clear. That is true, but it's hard to do because of the S insertion here. I haven't done that. There must be. I haven't done that. That's a good point. Yeah, I haven't done that. So Z was one of the source of the eigenvalue. That's why it's still a closed string guy. And this S came out of this open string degree of freedom. So we interpret that as the open string modulus.
And wait, sorry, integral transform over what? It's this ds you're saying?
Yeah.
Yeah, so you're saying that the d brain can be anywhere. And the determinant
Yes.
depends on where it is.
Yes,
Determinant of the off-diagonal words.
that's right.
That's your integrating. Your
That's the coupling between the off diagonal and the diagonal.
Yes.
Yeah, exactly.
And then you have to integrate over all positions.
Exactly. Yeah.
That's how
Sorry, but why dm integral doesn't depend on S? Where is the S dependent?
Here in the insertion.
Oh,
And it's very similar to even in the old matrix model literature, in this Seiberg et al. And Hashimoto et al. Papers. The FZZ brain is treated as a determinant operator, but that's not the same as this, in my opinion. That's for the old matrix model story. where they interpret them as macroscopic loop operators. And you get this again determinant insertion. This is something that just pops out of open-closed duality. I don't think they are directly related. Okay, so we want to claim that this is some extended closed string partition function and this is some open string partition function. And we had to really struggle to do this for a while. So this calculation is elementary. So the rest of the stuff of the work is to interpret each of these as some known quantities in the literature of integrable hierarchies. So I'm sorry if it bores you completely. You can stop anytime you're done with integrability.
Left hand,
yeah.
Left hand side here is
this.
Is that.
So I multiply this and divide by lambda to get this. Okay.
And that depends on lambda z.
Yes.
And is extended. There's something called an extended.
Yeah, I'll tell you in what sense it's extended in a few slides. See, this tau of lambda has a lot of special features that are not visible from the Kontsevich matrix model, but they're completely obvious from the integrability point of view. So I want to highlight these two features, and I want to say what happens more.
Tau is just partial function, right?
Tau is a partial function. So you see, the mathematicians will also have some ideas about how this, in the topological closed string theory, the tau of lambda was the partition function for this intersection theory on curves. But now you're Riemann surfaces with a boundary, right? Because you've introduced a d-brane. And so you have to ask, from the math point of view, what is this object? What are the properties of this? Because now you have an extra open string operator as well. Instead of sigma, apart from sigma case, now you also have an extra open string operator as well. So S is the coupling to that open string operator.
So is it really accurate to think of S as where the brane is?
Yes. So this FCZ has this boundary cosmological constant. So this S is related to that guy. And I think that is roughly where it ends in this Liouville direction, as you would say.
Where the brane is. Okay. So in Waffa and company's conjecture,
yeah.
Then even to make sense of what the right-hand side of the conjecture meant, you would have to know where you're putting your brane, right?
Yeah, I don't remember now in what they were talking about topological strings on Calabi-Yau's, I think, and they had some.
So maybe there it didn't matter.
Didn't matter, maybe.
So
yeah.
maybe in their case, this integral transform is somehow trivial. And
possibly, yeah, quite possible.
Maybe some saddle point also.
But I was thinking even more. I mean, even just to make sense of the conjecture,
You need to integrate over where the brane is added.
you need to know where you're putting the brane.
I mean, you may get dominant contributions of particular position.
But weren't they claiming an exact? Weren't they hoping for an exact result?
I think, yeah, I think so in their case. But it says maybe in their case it's a different brane. It's not.
Yeah, there's two possibilities that just to have sense of conjecture. Either there's only one place that you can put the brane, or every place gives the same answer.
I think the second one is possibly the right
Yeah.
answer. Yeah.
I also know. I'm sorry, this whole FZ story, but can you place it anywhere in the Liouville direction?
Yeah, so there's an open string modulus. They have a
It really is,
yes,
huh?
there is a
You really
modulus.
can.
Yeah.
Even though you have this wall and all that, and the dilaton is, you might think the mass goes like one over the other.
So it's pushed to the
Yeah,
bottom.
yeah.
That's like a zero brane and a one brane.
Yes,
right?
yes.
Oh,
And
one
ZZ is localized near the
One of
near
them is localized.
in the strong
The
coupling
ZZ
region
may
and
be the point.
is
Ah.
localized in the strong coupling region and yeah.
I see.
Okay, so I don't know what's going to come next. I don't remember now, but let's see. Yeah, so let me just flash back the slide of the Kontsevich model that I had earlier. So this was Kontsevich's claim that this tau of lambda is exactly captures this generating function of Witten in this fashion, and that, as we saw, these TKs are related to the matrix source by these traces. And I said some words there that the times TK are the times of this integrable hierarchy. And Witten's precise statement in one of his papers is that the tau of lambda is the tau function of a p-reduced Kp integrable hierarchy. So I want to explain what this means in a few slides for those who are not very familiar. So now I'm going to just change gear and just explain something about Mohammed was laughing already. Sorry. So you define the lax operator, which is a p-th order differential operator, and we consider the flow of this L with respect to some infinite times, right, with respect to some Hamiltonians. And if all the flows have to commute, then all the Hamiltonians have to satisfy this flatness condition, as I say. It's a condition that all flows commute. Now the claim in the integrability literature is that there is a natural basis of such flows which are generated by fractional powers of this lax operator. Okay? And the mathematical theory that goes into this is called pseudo-differential operators. So you define a formal pseudo-differential operator like so, where these I can have infinite number of negative terms but a finite number of positive terms. Okay? And then the A plus is defined as just the terms from 0 to n, positive powers of the derivative. With this definition, you can see that this L to the 1 by p has a natural meaning as a pseudo differential operator. So you just demand that the L to the 1 by p to the power p gives you this L. Okay, so that gives you a relation with all the infinite coefficients, and you can always solve these fractional powers if you work with pseudo differential operators. Now the claim is that the Hamiltonians that generate commuting flows are the positive powers of these fractional powers. Okay. Now, useful set of facts to keep in mind are that the first flow is clearly d itself. Okay, because you can see that if you take 1 by pth power, you'll get d, and you don't need anything else. And that you can get infinite number of d to the minus terms, but those don't matter when you consider the plus contribution. The second most obvious thing is that if you take k to be a multiple of p.
Sorry, just to get orientation. By flow, you've got space of Lagrangians. L is lax operator. Is it that?
Yes, L is a lax operator. So u is a function of x, let's say. So d is d by dx. All these u's are functions of x.
U's are functions of x. What is it? So some function.
Some functions of x. Now I want to extend them to functions of x and t.
X is what? X is one variable? Or
X is the variable the one variable you start with. And then you adjoin to x an infinite number of times, right? Generated by some Hamiltonians that commute, whose flows commute.
Is there a way of understanding it from integrability? What
This is it.
connection? So what should I identify H and with? Roughly to get some intuition. So what is my different Hamiltonians?
So, yeah, I will give you a few examples.
So what is the phase space?
Oh God, what is a phase space?
Yeah, in terms of, I mean, these H, there, how many Hamiltonians are there?
So here, no, infinite number of Hamiltonians. The infinite flows created by infinite Hamiltonians. You can just generate these Hamiltonians by computing this. There will be some.
These are the conserved charges which sort of, should I think about HNs as different conserved charges?
Yeah, they're the Hamiltonians, right? Yeah, they generate the flows, they commute,
Different
exactly.
conserved charges, and this is commuting, these charges commute with each other. This is the claim?
Yes. So the claim is that if you want them to commute, then H is satisfied this condition.
And H's are just differential operators in X.
That's right.
It's one variable. One simple. Okay.
No. Now, so you start. So you see, these H's are let me see. Let me just go ahead. I'm sure it will become clear with more equations. Give me a second.
Anyway, the commuting condition is clear just from
Commuting
the
condition.
second derivative.
Yes. So the first point is that, as I said, the first time is X itself. Okay. And the second point is that
Right,
whenever you have,
H never has a d by dt, right? It only has d by dx's. May have coefficients of functions.
yeah, now I'm going to identify X with T1.
These are the conserved charges.
X identify with T1 because you see,
Okay, fine.
yeah. So now you see what the second point is that H, whenever it's a multiple of P, right, then it does not generate any flows because you get a L. See, you have L to the NP over P is a power of L, and therefore it commutes with L. So those flows don't generate anything non-trivial.
Why, even if you have an integrable theory, why do you want your charges to commute? This is something I'm not understanding.
Okay, this is something we can take offline. Let me go ahead with this. We'll go offline with this. So the main point is that, so for instance, let's take P equals 2, which is the case for pure gravity. Then the lax operator d squared plus u of x. And T2 does not generate a flow because it commutes, like I said. If you write the equation for T3, then you see that the dl by dt3 will be this equation. And this is precisely the KdV equation. So this is why Witten would say that,
Prime is
d by dx always.
and T3 is the usual time in the KdV equation.
Exactly. So this time I'm defining like this. And the h is defined by like this from the lax operator. Okay? You can just, I wish I had time to work it out on the board, but I don't, so I'm just going to go ahead. How much time should I bother with time at all or no? You have a lot of time, great. Okay, so so you can generate flows this way from that lax operator. And there's a natural object which is defined to be the tau function of an integral hierarchy, which is defined to be the residue of this nth power of p. Okay? So log tau, so you should think of tau as really the tau of the partition function of the original matrix model. that we have. So log z is f, and this second derivative of f should be understood to be this residue of. So see, that's the relation between the f and the lax operator. If you set n to be, say, 1, you'll find that u that appears there is exactly related to this lax operator. So see, what I want to say is that the u that appears in the lax operator is like d squared by dx squared of log tau, which is like f. So the u that appears in the lax operator is related to the generating function in this way. Okay. So there are lots of other properties of the tau function that I'm not going to go to because it's completely out of our scope. But given the tau function, you can consider the lax operator.
Just to make sure I understand at all.
Yeah.
H3 is a differential operator only in X or not? I mean, that has d by dx but no d by dt anything.
No. All d by dt's are generated like this.
Right. So
What is the question?
H3
It's
has
just
d by dx.
exactly everything is only d by dx.
Fine.
Yeah. So you just take fractional powers, we'll generate all these d of x acting on the u's in the u case, right? Is this okay with people?
So this is a set of operators of differential operators of function of one variable. So very simple.
Right.
System.
Yes.
Labeled by many parameters.
That's right. So this generates a hierarchy of flows though. So these Hamiltonians are all higher and higher differentials of x on u's, and so they generate a whole hierarchy. And they are all put in the simple form like that. Okay. Good. So how to
The equation is the same equation you're showing us as second slide, right?
Yes. That was Witten's original conjecture that you see
But
that.
I'm trying to see how is geometry encoded in the right hand side of this equation, because over there you say the geometry is encoded in the right hand side of the KDB.
No, I didn't understand this.
The KDB equation you showed in the second slide,
Uh-huh.
you say that the information about the geometry of this 2D gravity theory is encoded on the right hand side. Maybe I just particular.
Yeah, maybe can we do this? Sorry.
So
Okay.
The fact that this is differential operator in X has to do with P equals to 2, right?
No, even for the higher p's, I think it will be the same.
So
Because there's just more functions of u's here. Higher p just means more functions of u. For p equals to add a single function,
Ti is now not on equal footing.
they are with the x, they are really. But yeah, this for us, the x will be special, as I'll show in a moment. Yes, so
Higher P's will be the other elements of the KDB.
yes,
Higher P's will correspond to synergistic equation.
I'm not going there. Okay.
Saying that for all higher P's, there are integrable hierarchies associated with those.
Yes, certainly, yeah. So you see, the thing you should ask yourself, okay, these are all differential equations, so what has this got to do with 2D gravity? And that has to do with boundary conditions. So KDB equations is very general. You know, they describe solitons, scattering, and so on as well. So it all depends on what initial conditions you impose to get out the partition function that you want. Right? So in a paper by the Digraph and Digraph-Witten, they showed that with this initial condition, right, the flows you generate will be such that the tau functions coincide with the tau function of the 2D gravity.
What is T here in the T3?
All higher t's, let's say. T except the first one is when all higher t's are set to 0,
All of them are set.
are set to 0, then you say that this is the initial condition.
I'm sorry, but
And now you evolve with the equation.
what was P? Sorry, does it preferred value for P?
No, P, so P equals 2 is pure gravity, and higher P would be some matter coupled to gravity.
I see. Some suitable.
Central charge less than 1 coupled to gravity.
So very simple, right? You just take this operator and act through these flows and you get the answer. Amazing.
Amazing. 30 years ago. Okay. Yeah, so with this initial condition, the claim is that the tau function is that of the Kontsevich matrix model. And you see, if you look at this matrix model, it's completely unobvious why the even times are missing. Because the claim is that T2n's don't appear in this partition model. And it's completely unobvious, and this was shown in gory detail in a long paper by Zixen and Zubair, where they explicitly calculated, they relate the d by d matrix variables to the d by d sources, and the d by d sources to this d by dt's. It's a lot of Schur functions and so on up here. So it's a hard calculation to show this, but you see from the integral point of view, it's very clear. So as I said, this is mostly to introduce a language of integrability. What I want to do is to, so this is okay, can I just move ahead from here? So I want to leave integrability now just want to use a lax operator and all these concepts at least once. So now I want to revisit our answer. This was our answer, right? Now I want to understand what these objects are in the language of integrability. Okay? You see, especially because in the algebraic geometric literature and so on, there are already candidates for the properties that open closed generative functions should satisfy. So what we have here is an explicit matrix realization of what we think is open and closed based on our string theory intuition. Whereas their analysis is purely formal, just like Witten could discuss modular space of curves, here they're doing modular space of curves with a boundary and using algebraic geometry. They have already results for how of the properties that these should satisfy, and ours have to match theirs. Otherwise, we have no basis to claim this.
Sorry to be so ignorant, but so the thinking is that you now look at differential forms or whatever in Riemann surfaces with boundaries and their moduli space.
Exactly. Yeah, I have not done that, but yeah, but there is a lot of literature on not a lot, but there are a few papers on this. And what I would like to do is to identify what we have found, which is completely explicit from a string theory perspective, as open, closed, and closed partition functions in this language. Okay, so what we have is, as I said, is a matrix interval representation of these abstract definitions. So let's see what they are, and let's start with the left-hand side. So you see the main, let me just go back one, sorry. The main thing is the tau of lambda z should be independent of all types that are multiples of p. Okay? But this factor clearly depends on all times. Okay? Because you see that this e to the xi is just t and z to the n with no constraint on all times. So clearly the left-hand side depends now on all times. So this is a sense in which it is an extended closed-string partition function, because now we introduce the extra times. And this is great because this is exactly what the mathematicians also say, that as soon as you introduce a boundary, the np times or the p times will be introduced into the game. The open closed partition function should depend on the extra time as well. And what we realized was that precisely this definition is what is called as a wave potential in an extended KP hierarchy by these two mathematicians. And if in case you are familiar with this, if I take a ratio of this tau extended with tau of lambda, the unperturbed one, the undeformed one, then this is already known to the physics literature as what is called the Baker-Akiza function, whose property is that it is an eigenfunction of this lax operator defined with the eigenvalues a to the p. Okay, so we have identified our left-hand side as something definite. Is partly why we made this identification.
So tau is obtained from tau external by setting z equals 0?
No, I want to say tau of lambda is the n by n guy, but everything in the large n limit. But yes, if you want, you can say that. Yeah, should treat this as a large n integral.
This Tx is this integral transformation that you showed.
Which one?
This tau x.
Tau external is no. Tau external is just this guy. The partition function times this renormalization factor. Yeah, LHS, exactly. It's a simple. So that's the first thing. Now for the open plus closed part. Now open plus closed part I define to be like so. And I will not work with this description at all. What I'll do is to understand this by using our previous left-hand side and the Fourier transform that I'm going to define. So you see our expression was this. So if I define this to be the open plus closed, then this is integral transform of this tau external, and this is the equation I had in my very first slide. So what we'll do is to show that if I take the inverse Fourier transform of this, then that satisfies all the properties that mathematicians have written down for open plus closed. Okay, so this is the question. This is our identification, and we want to prove that this is really is open plus closed partition function.
So the right hand side, you took the right hand side, made a integral transformation, and as an observation, you notice that this is same as the one that came from the left hand side. This tau external.
Yeah. So this was an identity. This was an identity. The only thing I did was to move one z-dependent factor to the left hand side and call that the extended partition function. Right.
You had this equation earlier. You had the left hand side, which is the closed string, and right hand side is open plus.
Yeah, but you see, this factor was not there on the left hand side to start with. I added this factor, and I said, now this should be the extended closed string partition function. Okay.
Did you rewrite this equation?
I've rewritten it in some way. That's it. Okay, so as I said, how do we know that this is the that the inverse Fourier transform of this is really the open plus closed? Again, we appeal to what is known about the result, and this lax formulation that I introduced is going to be helpful. So what people have done is the following. These are the flows I introduced earlier, same flows, written with bigger brackets, that's all. Now they define a wave function satisfying the following equation. So this capital psi is not what I introduced earlier. So you act with the fractional powers on this wave function, and the claim is that that defines the flow of this wave function. Okay? Actually, in principle, it can depend on all times. Okay? What mathematicians have shown using algebraic geometry is that this wave function is the generating function of the open plus closed partition function.
The wave function is a function of x and all the other things.
Not the other t's, but now all other t's as well. See, the TP also appeared. And their claim is that, so this is what they define using algebraic geometry, and they claim that that divided by this satisfies the equation of this sort. So our proposal is very simple. Our proposal is that if what we have is open plus closed, it should match this. Okay, so matrix realization open plus closed partition function should be identified with this, which means that whatever properties this should be satisfied by this.
So you have to show that differential.
Exactly. So what we have to show is that this inverse Fourier transform of what we have here should satisfy all the properties that the mathematicians have shown. And this is what we showed in the paper. I won't go through all the details. I'll just show you one check that we have done. Yeah, so this is our strategy. That we forget about this determinant insertion and so on. It's very hard to work with. We work with the left-hand side, which is much better understood. And then we take the inverse Fourier transform and show that this satisfies the same properties as what it is supposed to be. Okay, I hope the logic is clear. And the route we do is through this Virasoro operator. So this is something I haven't told you yet. There is a reformulation of all the KdV constraints in terms of Virasoro operators, which is the fact that
So this is not quite check off equation, right? Because
it's quite a check off.
so you're doing this to what end? To check your answer that it matches with the open closed partition function
From algebraic geometry.
in the
Yeah.
algebraic geometry.
Yeah.
So there you are not using the right. Here you are not using the right hand side
No.
at all.
But I'm using the integral transform and the left-hand side.
Yeah. Okay.
So it's not a direct check as you would like, but we did have an identity between these two. So if all the steps are correct, it's effectively the same thing. So yeah, so what we want to say, I'll show this in the next slide a bit more, but let me just say that, so this tau of lambda, we can show is killed by some Virasoro operators, but not all negative ones, just -1, 0, and then all the positive ones. And these ln satisfy the Virasoro algebra. So our strategy is going to be the following. We first want to understand how this acts on this extended set. Okay? And once we understand how it acts on the extended set, we will push this through the transform into an operator that depends on the open string moduli. And then we'll show that those trivially satisfy the Virasoro algebra. So what we have, therefore, is an open realization of the Virasoro constraints.
So is Virasoro now the same as the left one? So
No, I'll tell you about that in a moment. So let me just go ahead. So in the purely closed string case, the claim is that the same matrix integral tau of lambda is killed by these operators. And you see, they're all written in terms of t's and not the matrix versus lambda. But again, Itzix and Zubair have shown this explicitly using the matrix formulation. But this was already known earlier by Digraph, Verlinde. And you can see that all the t and p's are absent from these operators. Okay? So what we want to do is to first of all define an extended Virasoro that is allowed to act on this extended guy. So this we want to move this to some ln extended on this tau extended. So including the times tp at least. And then we want to show that we can push this through the Fourier transform in the right way. Okay, so I'm just going to give you the answer. So the answer is the following, that we make the following modifications in blue, where now the sum extends over all times. And we have some additions of tp explicitly here and d by dt and p explicitly here. And one can check that again, this satisfies the right Virasoro. Okay? So it's a classical Virasoro. So these satisfy ln, lm is just n minus n ln plus. There is no extension here. And all we want to do is to act with these guys on the left-hand side that depends on all the times and z, and write it as a purely operator on these. And you can do that because, see, the unshifted time, guys, kill the tau automatically. So this is how it makes it possible. And then the idea is to just push this through the transform, as I said, and write it in terms of S. So since we're getting so late, I'm just going to skip the details. I just want to say that, yeah, this is the strategy. On the prefactor, we know how it acts explicitly because prefactor is just the sum over t n z to the n, so we know how it acts on all the times. Tau of lambda z is just a function only of t tilde. So we use the fact that ln tilde will kill tau of lambda tilde, essentially. So the final result is that on tau extended, it acts as a differential operator on tau extended. So once we have this, you see, we can just shift these explicit differential operators through the Fourier transform and get a pure operator on S. That depends only on the properties of the Fourier transform. And so we can just convolve this operator with the Fourier transform function and just replace functions of z with s and d by ds. At least I hope the logic is clear. The details I don't expect people to follow. So you see, this is the operator we had, and if you just replace this with these substitutions, we find that we get the expected form of the Virasoro in terms of the open string moduli. So this is also a strong check on our proposed extended Virasoro. So this is what you would expect naively, at least the first term is what you would expect naively. And so these satisfy the open Virasoro. So we have shown that ln's closed can be moved to ln extended, and then we can move this through the Fourier transform and get ln open. So this is just restating it. I started with this, and we push these operators through the transform and show that there exists something called the open KdV hierarchy, which I haven't defined, but it should be equivalent to demanding that this operator kills your open plus closed partition function. Okay, we haven't shown that directly, but we've shown this through this Fourier transform business. And now I'm going to spare you the details. One can now, using these Virasoro operators, one can check all the checks that the mathematicians have that this guy really satisfies the properties for it to be the algebraic geometric definition of the open plus closed partition function. Okay, so let me just conclude with some remarks that gravity coupled to matter is well studied both from the math side and from the physics side, and our intuition was entirely based on the fact that we have an open string description of the closed string partition function. That was the crucial point. And once we did that, we just did a probe analysis of this integral, and we showed that we could relate a purely closed string partition function into a one with a shifted background via this Fourier transform. And what allows us to check our result is really this map to integral systems, hierarchies, and so on. So that's it. So this is the first few points I had is essentially these. Now you know what this means. A shift of the background means that t's get shifted, something that depends on z. Renormalization is by this factor that introduces extra times, and the integral transform is what it is. What I'd like to do next is to really do this from a string theory perspective. Really take, there is a CFT description of topological gravity that people have studied, the Berlin days and so on. And so we can literally introduce a boundary there. I mean, you really see if you can, do this, see this integral transform popping up, for instance. Or at least see the recursion relations that these would imply. That would be quite nice. So I'll stop here. Thank you for your time.
The mathematicians, every term in this equation is previously understood, right?
No, they have a, so let's see. No, they really work with this guy. They don't write it as a matrix integral as such.
I understand. But the answer, in terms of this moduli space of Riemann surfaces, if you could go one forward if you don't mind. This tau x z, zx, they have a suggested
lambda z on the left hand side, yes.
And also tau open plus closed lambda s.
They have it independent, yes.
So this is a new relation for the math.
Yes, I would
between
hope.
Two functions they already knew. They didn't know they were
different mathematicians knew these. Yes. I'm just saying.
Union of mathematics.
Yes. I would say
so. It's a new non-trivial identity between interesting mathematics.
Yes, I would say so, but yeah, but already for Buriak-Tesla, for pure gravity, they knew something like this.
Okay.
So it wouldn't be a surprise to them. I mean, pure gravity, they already did this by themselves. And you know, if I take p equals 2, ours doesn't really match theirs, but because they do a different way of integrating. So their matrix representation is different, but it's clearly the same thing. You just do it in a different way.
But you get a different identity, you're saying?
Yeah, I think so our right hand side is different from the known right hand side that mathematicians
Even
had.
for pure gravity, it's a new identity.
I would think so, I would hope so, but ours seemed hard to work with because it's determinant insertion, I don't know. Because for the mathematicians, they get a ratio of determinants in their case, and they have a nice way to expand it out. And then they explicitly check from them that for the pure gravity, the moduli space really comes out naturally.
Okay.
But we couldn't do that. So
We could hope that some mathematician will just directly starting from functions just prove this.
yes, you would hope so, yeah.
So for worksheet, you would expect this identity to work at the level of bounded conformity theory
I would think so, yeah.
at any given value of what is the model.
Well, first, yeah, I don't know if I try to prove this directly from the CFT point of view. What I'd probably try to do is to go back here, look at the math definition, and try to see what recursion relations they imply. See, the equations, all of these equations, they relate correlators of sigma and naught and so on, right? They have these. So what the KDV hierarchy and all these things imply is a recursion between these operators at higher genus, lower genus, less number of insertions and so on. Now you have some operator O to some K. Right? This is the open string operator. What I would first do is to try to first see if we can recover the recursions for the open string inclusions, and then try to do this afterwards, I would say.
I'm asking a simple question. So when you write down the worksheet theory,
Mm-hmm.
and you're considering some correlation, let's say, with some open string vertex operators also considered,
Yes.
then would you then expect that at a given, even without doing the worksheet integral,
Uh-huh.
just
Oh.
the level of the CFT, that this open string partition function should be rewritten in terms of less number of branes and with some modifications which will be
I would, yeah, but then you would need to know the exact boundary state. Yeah, I guess it should be possible since it might be possible. I don't know if the branes are known in the language of topological gravity. The branes are known in the string theory point of view with the Liouville times matter. Yeah, but in this, that would be a good question. Actually, that's a good question. Yeah. So what is the FCC brane in this language of topological CFT for topological gravity? Yeah. Once you know that, then I would agree. Yeah. We were just going to try to do something order by order, adding a few open string insertions and seeing you can recover the recursions that they already have in the math literature. But yeah, ideally yes.
In a physical situation, if you had n brane, you separated one and then you did an integral over all of them, you'd get a divergence when this guy hit one of the other branes. Is there anything like that?
No. I don't see it anyway, yeah.
It would be this factor that integrating out.
Oh, sorry, you're right. So you're saying that when the eigenvalues coincide, what happens? Determinant S, but no, it's fine. There's a shift by lambda. Let me see where it is.
I mean,
There.
roughly speaking, you would be integrating, in a physical
This
situation,
one?
you'd be integrating out a massless mode.
Yeah.
And that's something you're trying to avoid doing. I was just wondering whether there's some analog of that.
Yeah, so you're saying I'm integrating over S is an S integral and there is this M integral and you're saying M minus S is there. What happens when S approaches one of the eigenvalues?
Yes.
Yeah, so then you see it's like you have an n by n matrix somehow. No, you're saying
If you're just doing a matrix integral, it sounds like you're getting zero rather than infinity. Right? Because isn't this where the Vandermonde vanishes?
that's true.
So it sounds like you're fine. It sounds like the contribution from one an eigenvalue coming very near the other goes to zero.
What happens to the denominator then? Is that the same as well?
Does the denominator depend on S?
No. Yes, right? No, it doesn't memorize like that. No. I've already done the integration over. Yeah, no. This is what it is. No, I think it's a good question to ask. You can ask it here. Yeah, you're right. So you're saying that Vandermonde vanishes?
So it doesn't look like there's a dilemma. I mean, if that's the only factor that's important, it doesn't look like there's a problem. In a more complicated situation, you would expect there to be a real degree of freedom here. It becomes massless. then you're integrating out of massless mode, and you're doing all the things one shouldn't do. And then I was just trying to think, from the point of view of n equals 4 angles. Let's say on a sphere.
Yeah.
I'm not so sure because there's a model like okay, but I was trying to think what
is the analog of this?
what is the analog of this? Right? There are many issues.
Yeah. Yeah, I don't have anything
Okay.
insightful to add. Sorry.
Any more questions? No, let's thanks.
Thank you.